Good day everyone. So for today, you're going to learn another new type of first order differential equation, and that is the exact differential equation. After you have established that it is an exact first order differential equation, you will learn how to find its solution. So first and foremost, we will define in terms of form what a particular exact differential equation should be. So our DE should be first written in the form in which you have two terms. One term has the differential of x and the other term has the differential of y. Now, in this particular form, your DE is said to be exact if we follow this particular theorem. So the theorem says that the m here and the n here, same thing with the partial derivative of the m here with respect to y and the n with respect to x should be continuous. Meaning, if we substitute a value for the variable on the said expressions, our answer should be something that is existing. Meaning, it's not indeterminate or it's not infinity. The second condition is the partial derivatives of m and n with respect to y and x respectively should be equal. So even if these two expressions are continuous, meaning their values are real, their values are acceptable, and this partial derivative condition is not met, our DE is not yet said to be exact. Now, the differential equation of the form m of x and y dx plus n of x and y dy equal to 0 is an exact differential equation if there exists a function f in which m of x and y dx plus n of x and y dy is equal to 0. So this f here is the solution of the said exact DE after you have already determined that it is exact, or that is after you have already tested that your DE is exact. Now, it says here that the partial of this solution, the partial derivative of f with respect to x is the m here, which is multiplied to the differential of x, and the partial derivative of f with respect to y is the n here, which is the multiplier to the differential of y. Again, I will repeat, the f is said to be the solution of our first order exact DE. So it's a two-part procedure, just like homogeneous DE. You need to test whether your DE is exact. After you have already tested and established that your DE is exact, then your next goal is you find the solution, which is the F. Now we move on. So there are 2 or 3 methods available, so probably 2 would work already in determining the F. And that is the solution of your exact DE. So the first method is this. You need to integrate the partial derivative of f with respect to x holding y constant. So again, integrate the partial derivative of f with respect to x considering the other variable y constant. And that should be done by this. Then again, you need to integrate another expression, and that expression would be the partial derivative of f with respect to y, and in this integration process, you will hold the x variable constant. Now, you will have two answers. What you do, term by term comparison, that is, you compare your answers for A and B, and then you get out or you select the terms that are present in both answers, and that would be the solution of your DE. That is for method 1. Anyway, you will have a specific example later on how this is done. Now, this is the example that I'm going to give you regarding method 1. Now, let's say for example, in this DE, 2xy dx plus quantity x squared plus 3y squared dy is equal to 0. We'd like to test first whether this DE is exact or not. Now again, the 2xy is your m of x and y. The quantity x squared plus 3y squared is your n of x and y. This m is the partial derivative of f with respect to x, this one, and This n is the partial derivative of f with respect to y as defined in the previous slide. Now, we are going to test. So, we will get the partial derivative of f with respect to y, and that would entail differentiating it with respect to y only, considering x a constant just like any number constant that you are seeing. So, the partial derivative of m with respect to y is 2x. That is for this one. Now, if we get the partial derivative of n with respect to x, we will consider the y constant. So, this would be done in here. Partial derivative of quantity x squared plus 3y squared will be partially differentiated with respect to x. Now, since y is a constant and it's together with the constant number 3, the derivative of the entire second term here will be 0. That leaves you only to differentiate x squared in terms of x, and the answer is 2x. Now, look very closely as to the partial derivatives of m and n with respect to y and x respectively. They are equal. If they are equal, then our DE is said to be exact. When your DE is exact, and if you're going to use method 1, it's very easy. What you're going to do, you go back to your m here, which is actually the partial derivative of your solution f for this DE with respect to x. And that is here written. So, partial derivative of f with respect to x is actually your m, which is 2xy. You need to integrate this expression with respect to x, considering y a constant. So, if you are going to integrate in terms of x, then the variable that you should be only integrating in this expression is the x. The 2 and the y are to be perceived or considered as constants. And that would give you, by power rule, x squared over 2, which will cancel out the 2 here, giving you the integral of this expression as x squared y. Now, you do the same for the n, but this time you will integrate it with respect to y. So, again, you have copied the n here, and you will partially integrate it with respect to y, considering x a variable. If this is a variable and you're integrating it with respect to y, your answer will be x squared y, because you simply copy constants when you integrate. Okay? The x variable here is a constant. So, you copy it, and the y is coming from the integral of the partial differential of y. If you integrate the 3y squared in terms of y, that would be 3y cubed over 3, canceling out the 3. And that should give you a y cubed. Now, in comparison, look at the terms that are present in your solutions. You have two solutions here. That from the integral of m, and that from the integral of n. So, you have a common term, which is x squared y. You copy that. And you have another term, which is y cubed. So, these two terms now will be the solution of this given exact first-order differential equation. Always, we write the arbitrary constant of integration on the right side of our solution. There is one thing to be noted here. When you do the testing, class, so take note, when you do the testing, you partially differentiate m with respect to y. But when you do find the value of the f already, that is when you integrate it with respect to x. The partial derivative of n is with respect to x, but when you integrate it, it's already with respect to y. So they are the inverse of 1. But you will not really get confused because your f, the partial derivative of f specifically with respect to x, is the m here, which is multiplied to the differential of x, the variable that you are seeing on the differential. That is also the same variable in which you're going to integrate this. But when you do the testing, it's the other variable that you partially differentiate it with. So, m is partially differentiated in terms of y, n is partially differentiated in terms of x. Now, we move on to the other methods and to other examples. Now, method 2. You still need to integrate the partial derivative of f with respect to x, considering y a constant, and you will, of course, integrate only in terms of the variable x, and you will have this answer. Now, your arbitrary constant will be the g of y. So, take note, you have an arbitrary constant here, g of y. Next is you differentiate f with respect to y and equate to n. The answer that you have here, the answer that you got here, you will differentiate in terms of y. The answer that you're getting here, you will differentiate in terms of y, and then you equate it to n, the n in your original DE. What's the purpose of equating? It's for you to get this g of y. Once you have the g of y, you place that, or you substitute back the g of y to the answer of the f when you integrated it with respect to x. Now, quite complicated compared to method 1, but it's actually easy to follow. Let me give you a specific example. Here, you're given m as 3x squared y if you're going to distribute the 3x to xy minus 2, and you have a negative 6x here. Okay? Your n will be x cubed plus 2y. So, we simply distributed the 3x to the quantity xy minus 2 in here. Then, just like what we did in the first example, you need first to establish that your DE is exact. So, find the partial derivative of m with respect to y considering x constant. So, the derivative of 6x will be 0, and this 3x squared, which is all considered a constant, will be the partial derivative of m with respect to y. Now, n will be partially differentiated in terms of x, so the 2y will be a 0 because y is a constant just like 2, and x cubed will be 3x squared when partially differentiated with respect to x. Now, since the two are equal, we conclude that our DE is exact, and we will this time follow method 2. Just like method 1, you need to integrate the m, the expanded m, with respect to x. So, I copied the one that we have here, place it there, and we integrated this with respect to x. The answer will be x cubed y. Why? Because the integral of 3x squared is 3x cubed over 3, canceling the 3. Y is a constant, so you simply affix it to the x cubed. Now, you have the appearance here. So, you have the appearance of the g of y. So, you have 3x squared y minus 6x. Now, where is this coming from? So, x cubed y minus 3x squared plus gy. Where is this coming from? You differentiated f. You integrated rather your f here on top with respect to x. So, this is our answer. Okay? X cubed y, that would be for this, and the 6x when integrated will give you a negative 6x squared over 2. So, the 6 will become 3. The c is replaced by the g of y. Now, next procedure under method 2 is you will differentiate with respect to y and equate to n your f. So, the answer that you have on top, this is your n by the way, x cubed plus 2y. That's your n. You will differentiate your answer here, with respect to y. So, if you differentiate, that would be x cubed because y is your constant, and this will be 0 because x is a constant. And of course, the derivative of g of y with respect to y is the g prime of y. Okay? So, after integrating your f with respect to x, you will differentiate this with respect to y. Partially differentiate specifically. And this is your answer. And then you equate it with the n that you have in here. The purpose is for you to get the value of the g of y. So, if you equate both sides, the x cubed get cancelled. Remaining expression is g prime of y equal to 2y. And you integrate the g prime so that you will have the g of y. If you integrate this side, you need to also integrate the other side. So, g prime of y when integrated will give you the g of y, and when integrating 2y, that will give you y squared. This tells you, class, that the g of y that appears in the first procedure that you have done is actually having a value of y squared, or is equal rather to y squared. So, the solution of your DE now will be this x cubed y minus 3x squared plus the g of y which you have determined here. Again, the constant of integration c is written on the right side. So if I will summarize, method 2, test first. So partial derivatives of m with respect to y should be equal to partial derivative of n with respect to x. After testing, integrate the m expression with respect to x. So you have the answer already. Replace the arbitrary constant of integration c by the g of y. The next thing you do is the answer that you got in A, you will partially differentiate with respect to y. That's done here. And then you equate that to the given n, which is the x cubed plus 2y. The purpose is for you to get the g of y. The g prime of y is integrated to give you the g of y. Excuse me. Then once you have already the g of y, you go back to the original expression you got from the integral of the partial derivative of f with respect to x, and that already gives you the solution of the DE using method 2. If you recall, I said you will have around 2 or 3 methods because the third method is just the opposite of the second method, or it's just a copycat, or in terms of pattern, it's the same as method 2. So let us go forward. So let's go on to the next slide. Method 3, you will integrate this time not the function of f with respect to x, but rather the function of f with respect to y. And that is your n. You will integrate it with respect to y. Okay? You will consider x as a constant. Then your answer here will be differentiated, that is specifically partially differentiated with respect to x. Your answer will be equated to m so that you will be able to get the f of x. So it's the reverse of method 2. So let's look into another example. The same DE is given. You have this as your testing. This time you will not integrate the partial derivative of f with respect to x, which is your m. This time this one you will integrate with respect to y. So we do that. If you integrate it with respect to y, you will have an x cubed y, and for this one that would be 2y squared over 2, canceling the 2. Take note that your c is not g of y, but rather f of x, because this time you are partially integrating with respect to y. Now your answer here should be partially differentiated with respect to x. Okay? Partially differentiated with respect to x and equated to m. So if we do that, this one would have a partial derivative of 0 with respect to x because this is a constant. While this one will be 3x squared when partially differentiated with respect to x. 3x squared y. We copy the y. So we have it here. So partial derivative is 3x squared y minus 6x. For the m, we copy. And this one, when differentiated, as I have mentioned, is your 3x squared y plus the f prime of x. This is the expression that you got when you partially differentiated your f here in A with respect to x. So this is it. This one is your m. So we don't equate with respect to n, but we equate with respect to m. Now, we cancel the 3x squared y in both sides. That would give us f prime of x equal to negative 6x as the remaining terms. Then we integrate so that we convert the f prime of x to f of x. And that should be negative 3x squared. This is your f of x, meaning you substitute negative 3x squared here, and that would give the solution of your DE already. So you have an x cubed y plus y squared minus 3x squared equal to c. This is the solution of this DE using method 3. Method 2 and method 3 are just the same in pattern, only that we interchange the manner in which we do the integration and the partial differentiation part. So we have a 3 method for exact DE, for the treatment of exact DE. Just like homogeneous DE, you need to test first before you do use the procedures discussed here. So if you have any question, drop a question or comment or suggestion in the reply blocks in the discussion part of your canvas. I will place this under discussion so that should you have any question later, you can place it under the reply box in the discussion area. So I will be uploading 2 videos that would be for the homogeneous differential equation and the exact differential equation. On Friday, you will have one for another one or 2 for determining the integration factor and the linear and Bernoulli equation, because after this week, after next week rather, it would be exam already. And we need to cover everything in terms of first order differential equations and their solutions for prelim. Don't hesitate to drop me a question, place a question in the GC, or write me an email if there's something that is not clear here. I will also put files of this slide in our Canvas so you can recheck and you can listen to this video together when you are in your process of studying. Please don't forget to go over the problem sets I gave you to solve. You can already solve the part on separable, homogeneous, and exact differential equations. That way, when it's time to submit it, you won't have a lot of things to practice solving again. So that particular problem set, by the way, is to be submitted in groups. The groupings that you have submitted in our group chat. Happy learning, class. Drop me a question or a line if you cannot understand anything pertaining to what I've discussed today. Thank you for listening.